Hi everyone, it's Mr. Grant here. Today we're going to continue our topic, Hess's law, and we're going to look at a type of reaction called a formation reaction. And by the end of today's lesson, you should be able to find the enthalpy change of any reaction that you encounter using formation reactions, which can be easily looked up online in your textbook or from a variety of other sources. So what is a formation reaction? Okay, a formation reaction is a reaction in which 1 mole of a substance is formed from its elements in standard state, right? So when we think about most substances, they are compounds that contain multiple elements. So if we were to build up that compound from its individual elements in their standard state, we would have a formation reaction. Okay, so these are all going to be synthesis reactions because they only produce one product. Okay, so many common nonmetals are diatomic molecules in their standard state. So if we were to build something from the elements hydrogen or nitrogen or oxygen and so on, these are going to be built from these diatomic molecules. And that's what they exist as in their standard state. The other elements all exist as monatomic substances where we just write the symbol with no subscripts. Okay, so here's an example of a formation reaction. Hydrogen gas, which is diatomic, reacts with oxygen gas, which is also diatomic, to form H2O as a liquid. And note, in order to balance this to produce only 1 mole of H2O, which is the requirement for it to be a formation reaction, we need to use half a mole of O2. So previously we would try to balance these using whole numbers only. For these types of problems, it's okay to use fractions. The important thing is that the product that's formed is only a single mole. Okay, so we'll use whatever fractions we need to balance them. Just note that state symbols are also important here because the elements that we're making these out of must exist in their standard state. Here's another example. To make CH4 from its elements, well, we would need carbon, which exists as a solid, and hydrogen gas, which is diatomic. Balanced, that would be 1 carbon and 2 H2s. Let's look at a few examples that are not correct and see if we can figure out why. Okay, here we have solid carbon reacting with oxygen atoms to become CO2. At first glance, this is balanced, everything's in the right state, but if we look a little harder, O does not exist as atoms in nature. Okay, so the correct way to write this would be carbon plus 1/2 O2 to make CO2. Okay, remember, oxygen comes in pairs in nature. Here we have H2 and F2 reacting to make hydrogen fluoride. Okay, again, it's balanced, everything's in the right state, looks good. The problem is we are making 2 moles of a product instead of 1. Remember, the requirement is we only make 1 mole of each product. So we're going to just cut everything in half. Half a mole of H2, half a mole of F2 to make 1 mole of F, or of HF. That's better. Okay. Here we have sodium ions reacting with chlorine ions to form NaCl. This is actually a specific reaction called a lattice formation reaction, but it is not a standard formation reaction because sodium and chlorine here are written as ions. Okay, they should be written as their elemental form. For sodium, that would just be Na with no charge, but as a solid, not as a gas. And chlorine exists as diatomic molecules, so it's going to be 1/2 Cl2. Okay, so these would all be formation reactions. Okay, so to recap, the requirements for something to be considered a formation reaction: 1, all of the reactants must be in their standard state. 2, only 1 mole of product is formed. And 3, the product really can be in any state and it can be any product. It doesn't have to be standard. Okay, so we didn't say that explicitly, but that's true. All right, let's do some practice problems. Let's write the enthalpy of formation reaction for ozone, O3. Note O3 only contains one element, which is oxygen, but O3 is not the standard form for oxygen. The standard form is O2. So to make O3, we would need 3/2 O2 to make 1 mole of ozone. The enthalpy of formation for this is positive 142.7 kilojoules per mole. This is something we could look up online. I want you to note the symbol for enthalpy of formation is delta HF, And then typically we would put parentheses with the substance that is being formed. Okay, here we have hydrogen as a liquid. Again, hydrogen contains only one element, H2, but liquid is not its standard state. So its standard state is a gas, so we would need to convert it from a gas to a liquid. This is not quite a chemical change, but it's a physical change, and it does involve an energy change. The enthalpy of formation of H2 liquid would be negative 449 kilojoules per mole. Here we have glucose. Looks pretty big, but again, we can just break it into elements. This contains carbon, hydrogen, and oxygen. We would need 6 carbon, 6 H2s, and 3 O2s to make 1 mole of glucose, which comes at an energy release of negative 1274 kilojoules per mole. Lastly, we have iron as a solid. Okay, this is an element. It is already in its standard state. So this formation reaction, solid iron becoming solid iron, it's not really a reaction. The enthalpy of formation for iron then as a solid would just be 0 kilojoules per mole. Okay, key idea here, the enthalpy of formation of all elements in their standard states is 0. Okay, they already exist in their standard state. We don't need to put any energy in or take energy out when we're converting them. So let's see if we can put this all together to get something useful out of it. First, all reactions can be written as the sum of formation reactions, and formation reaction enthalpies are readily available online, like Wikipedia. So, using Hess's law, we can find the enthalpy change of any reaction by writing it as the sum of formation reactions. Any reaction can be rewritten as the formation reactions of the products minus the formation reactions of the reactants. So let's see how this works in practice. So let's see how we can rewrite a reaction using only formation reactions. So here we have a combustion reaction where CH4 reacts with oxygen to produce CO2 and water. This contains 3 compounds that are not in their standard state, CH4, CO2, and H2O. So we're going to need the 3 formation reactions for those 3 substances. Let's start with H2O. H2O is a product, but 2 moles of H2O are formed. So we're going to need to multiply the formation reaction by 2. The enthalpy of this reaction is negative 285.8. So when we multiply this by 2, we also are going to multiply the enthalpy of that reaction by 2. Next, we have CH4, which is a reactant. Because it's a reactant, we're going to need to multiply the formation reaction by negative 1 to swap the sign. Again, this will also swap the sign of the enthalpy change from negative 74.6 to positive 74.6. Lastly, we have CO2. CO2 is a product, and we only form 1 mole of it, so this is good as is. We don't need to do anything regarding multiplication here. Okay. When we sum all of these together, we have this big guy. Okay, but if you're like me, you like crossing things out, you'll see there are a few things we can cross out here. For example, there are 2 hydrogens on both sides, which can be canceled out. We also have 2 carbon on both sides, which could be canceled out, and those 2 O2s on the left side could be combined to give us our original equation, CH4 plus 2 O2s as reactants to produce 2 waters and 1 CO2 molecule. To find the total enthalpy of this reaction, we sum up all of our individual formation enthalpies, multiplying them by their stoichiometric coefficients. This yields negative 890.5 kilojoules per mole. So that's the energy released when methane is combusted. We can calculate that using only these formation enthalpies without actually having to test it out in real life. So I want to show you a summary, a way that we can do this very simply. The enthalpy of any reaction can be rewritten as the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. Going back to our original example, here we have CH4 and O2 as reactants, and CO2 and H2O as products. Okay, we have our expression, enthalpy of reaction is the sum of the formation of products minus reactants. Okay, the sum of the products here is going to be the enthalpy of formation of CO2 plus 2 times the enthalpy of formation of H2O, because we're making 2 moles of H2O. From this, we would subtract the enthalpy of the reactants. The enthalpy of formation of the reactants would be the enthalpy of formation of methane plus 2 times the enthalpy of formation of O2. But remember, O2 is an element at standard state, so that's actually going to cancel out. To find these values, these enthalpy values, we would use a standard enthalpy of formation table, like this one taken from the textbook. If I were to look up the different values, I could find methane, CH4 is on here, the enthalpy of formation of negative 74.8, CO2 is 393.5, and H2O. H2O can be kind of tricky. You'll see at the bottom you have water and water vapor. Typically reactions involve liquid water, so we would use negative 285.8, but you want to pay attention. I didn't write the state symbols here just to keep it clean. So I encourage you, try to use this table to see if you can get the original value that we got, which should be around 891 if you find the correct values. All right, please let me know if you have any questions via email or on Google Classroom. Have a good one.